Good evening, everyone. So this is third live session for our CFD course. So in today's session also we will be seeing few of the problems and see how it goes. Welcome you all to the live session 3 for the computational fluid dynamics course by Professor Srinivas Jayanti in NPTEL. So in today's problem, the first problem is so in this question, it is asked like questions for this assignment have reference to the following three figures. Choose the correct answers from the options below. So three figures are given. From this, we have to choose the correct answer. I mean, from these, the questions will be asked. We have to solve those questions. So the first question is, you wish to compute the steady laminar fully developed flow field through the triangular duct shown in figure 1. For this case, the governing equation is given by. So this is the figure 1. In the question, it is asked like for the steady laminar fully developed flow field through the triangular duct, what is the governing equation? So in general, the governing equation are like continuity equation and the momentum balance equation. So for the steady laminar fully developed flow, the continuity equation becomes like this, and the momentum balance equation reduces to this format, where the flow will be considered in the one direction and all other terms like steady state terms will be reduced. So from this it is like del dot u is equal to 0, or from the momentum balance equation it will become like del dot del u is equal to constant. So in this option it is given that del dot del u is equal to 0. This is false. Del dot del u is equal to constant. This answer is the right one. Del dot del u is equal to minus del p. This is also false. Because here mu will come in this term if it is equal. So moving on to next question. You wish to compute the steady laminar fully developed flow field through the triangular duct as shown in figure 1. For this case, which of the following is an admissible governing equation? So the first equation, it is given that dou square u by dou x square plus dou square v by dou y square is equal to minus 10. And in second, it is dou square u by dou x square plus dou square u by dou y square is equal to minus 10. Third, it is dou square w plus by dou square dou x square plus dou square w by dou y square is equal to minus 1 by mu dou p by dou x. For this case, three forms are given and we have to find the right one. So the governing equation in this term, it is like dou square mu by dou x square plus dou square u by dou y square plus dou square u by dou z square. It is so the first term, it is not like dou square v by dou y square. So the first term is false, and also like here it is the other term is not given in z and all. So that this also becomes false. Whereas in 3 it is given that this is a proper governing equation for this term, but it is like dou square w by dou x square plus dou square w by dou y square is equal to minus 1 by mu dou p by dou z should come. It is not like dou p by dou x. So the answer to this question is none of the given following equations are right. So the none of the above is the correct answer. And we'll move on to question 3. In question 3, it is given that you wish to compute the steady laminar fully developed flow field through the triangular duct as shown in figure 1. For this case, which of the following equations is applicable? Del dot u is equal to 0, del p is equal to 0, or del dot del p is equal to 0. We have seen previously that from the continuity equation del dot u is equal to 0, and from momentum balance equation del dot del u is equal to constant, or del p is equal to constant. So since del p is constant, del dot del p is equal to 0. Del p is not equal to 0, but it is constant. So options 1 and 3 are right. So from this, third option is the correct answer. That is 1 and 3 is right. In question 4, it is given that you wish to solve for the velocity field for fully developed flow through the triangular duct using the grid as shown in figure 2. You discretize the governing equation using finite volume method and obtain a set of linear algebraic equations. How many algebraic equations will you need to solve simultaneously if the walls have zero velocity boundary conditions? So in this, it is given that for figure 2 is considered for this problem, and in from figure 2 we should they have given that we should discretize them using the finite volume method, and how many algebraic equations that needs to be solved at the end of the problem, that is what is asked in this question. So in finite volume method, there are few things to be considered in finite volume method, like the direction cosines like nx and ny will be considered for the side in the outward normal direction for each side that is considered, and the direction cosines are obtained from the geometry of each side, while the gradients are evaluated at midpoints, that is dou w by dou x. All these things are evaluated at the midpoints, while the direction cosines are evaluated at the each sides. Uh, and while the gradients are obtained evaluated at midpoints of each side using values of the cell and those of the boundaries neighboring cells or the boundary conditions. For example, if we are considering this cell, we will be considering the directional cosines in these sides, whereas while calculating the gradients, we will be considering between this cell and this cell, or this cell and the boundary conditions, and so on. So in finite volume method, it is like the directional cosine into the gradient, that is will be uh, summed over all the cells, and it would give the product of the constant C and the area of the cells when it is multiplied by each individual cell. So for this problem, this is figure 2 is considered. So we'll see how many equations we can frame if we are solving all these. If we are using finite volume method to solve all these equations. So to discretize all these cells. So basically, the first thing is this is the given cell. So for example, if a problem like this is given, we should know the midpoint of all these cells or the centroid, and for simplification purpose, we will put access points for all these individual cells separately. We'll consider this to be two in dimension for each cell, so that it is 0, 2, 4, 6, 8. I'm sorry, the points are reversed. Sorry for the trouble. Like x and y axis are reversed. But in general, like we'll put this would be 2 comma 0 to 4 comma 0 and so on. Sorry for the trouble, the points are x and y axis are reversed in this case, but the concept wise we put the grid points for this, and we name the cells 1 2 3 4 5 6 7 8 9 and 10. So for we know the midpoint of the square, like we know it to be like, if it is 2 in dimension, this would be like 2 into so it would be 1 comma 1. So but these are all corners are all triangular in shape. So to get the centroid of the triangle, we use a formula like x1 plus x2 plus x3 by 3. Similarly, y1 plus y2 plus y3 by 3. So by using that, we will get the centroid of this triangle, this triangle, this triangle, and so on. So for in the same manner, like we have obtained the centroids x and y for all these individual cells. We'll see few cells and we'll understand how it is formed. For example, in this is cell 1, this center point is 1 comma 1. So it is given 1 comma 1. If it this is cell 2. In cell 2, this would be like 2 comma 0 and 2 comma 4. So the x-axis point would be 3. Similarly, the y-axis point would be 1. So it would be 3 comma 1 for the cell 2. For getting the centroid of the cell 4, what we must do is we should sum up all the points in the of these vertices, so that for x-axis it would be 6, 8 and 6. So it would be 6 plus 6 plus 8 divided by 3. That would be around 20 divided by 3, it would be 6.67. So for x-axis it is 6.67, and for y-axis it would be like 0, 2 and 0. So that would give 2 divided by 3, but it would be 0.67. In a similar manner, we have formed the centroids, found the centroids for all these cells, so that can be used in the calculation. So we'll see three main cells. The calculation further would be based on all these, like it would be repetitive of all these. So for example, what we are going to do in this finite volume approach is we are going to multiply the direction cosine with the gradient, that is nx or ny into dou w by dou x or dou w by dou y. That is what we are going to do. So this is cell 1. The cell 1 is this. So first we will do the finite volume approach for this cell. When we are doing finite volume approach for this cell, the direction cosines would be, these two would be in y direction, and these and left and right would be in x direction. So this is in -1, and this is +1, this is +1, this is -1. The direction cosines are fixed for this, as I mean for the square cells, square or rectangular cells as this, when they are not inclined. So we have for this condition like -1 comma 0. This is cell 1. Left of this cell we do not have any cells. So it is w1 dou w by dou x, right? So it is w1 minus 0, and in a similar manner it is 1 minus 0. That is, since there are no cells, we are using the boundary points 1 minus 0. And in for the right we get like this is cell 1 and this is cell 2. So we are using the midpoints. Like this is 0.1, that would be 0.3, the midpoint of the next second cell. So that is 3 minus 1 and w2 minus w1. So we'll get the x and y, nx into dou w by dou x plus nx into dou w by dou x for this and this coordinate directions. And similarly for this and this direction, we'll get the values as, for if we are going in the top direction, it is 1 into the cell above this is fifth number 5 cell. So that is w5 minus w1, and y-axis value in that point would be, this is 1. So the midpoint of that cell, that is the centroid of the cell, would be 3 minus 1. Here we are using the centroid points. That is a point to be noted here. And for here it is minus. So we are using w1 minus 0 and 1 minus 0. Since we are not having any cells, we are using the boundary points. And is equal to a constant c into the area of the cell. Since these are 2 in horizontal and 2 in vertical direction, the 2 into 2 gives 4. So this is one equation. If we simplify this equation and put it in a form, this is one equation. Another, like the square cells would follow the same manner. So we'll see how to simplify or a problem for a triangular cell. For example, consider this cell 4. So in order to simplify this cell, we will be getting like it is 6 and 8 in the, like since it is the last cell and 8 in points, I mean 8 in dimension, the coordinates, x coordinates are 6 and 8. And while the y coordinates would be 0 here and 2 over there. So we can put the direction cosines nx and ny for this. So putting it, we'll get this nx as -1, and this is fourth cell. So W4 minus W3, that is the next adjacent cell. And the centroid of this cell, we have calculated it to be 6.67 by summing up all the vertices. So we get the 6.67 and the neighboring cell midpoint is 5. So this is for this direction. And similarly, in this downward y direction, we get this as minus 1 into W4, that is this cell, minus 0. We do not have anything. And similarly, the centroid point for fourth cell is 0.67. So we get the 0.67. 0.67 over here. And for this side, for solving this side, we have the direction cosine in this direction. So we have to resolve it in the two directions, x and y. While doing so, we get the values in these two directions to be like, if it is the point, we get the if we put sine 45 and cos 45, we get the value direction cosine normal to this is 1 by root 2. So this is 1 by root 2, and W4, this side it is not, I mean no cells are there. So W4 minus 0 for this horizontal direction, and it is 6.67 minus 7. That is, this is the point, maximum point, that is we are using the boundary. So it is 6.67 minus 7. On using this, we get the equation. And similarly, we should resolve in the vertical direction too. In vertical direction too, we will get the 1 by root 2 into W4 minus 0. And W4 minus 0, we get it is 0.67. And the midpoint or the boundary point would be 1. So it is 0.67 minus 1. And for this, the area would be half into height, base into height. So it is half into 2 into 2. So that gives 2c. So this is a solving for cell 4. That is, we have seen how to solve for this, These two cells would be similar to this, and these two cells would be similar. These 9, 7 and 4 cells would be, 9 and 7 cells would be similar to 4. 8 also would be rectangular one, so it would be simplified. We'll see how to solve for the cell number 10. In cell number 10, we have got really sorry, this is 0, 6 and 0, 8. And this is 2, 6. Sorry for all those. It would be like minus 1. So in this direction, we would get minus 1. W10, this is cell number 10, minus 0. And this would be 0.67 minus 0. Like, since we are getting 0 and the centroid of this cell number 10 would be 0.67 in the x direction and 6.67 in the y direction. So it is 0.67 minus the boundary point is 0. That is W10 minus 0, 0.67 by 0. And then similarly for y direction, we get that minus 1, that is ny normal. Normal is minus 1, and W10 minus the bottom cell is W8. So it is W10 minus W8, whereas in W10 the centroid point is 6.67, and in the 8th cell the centroid point would be 5. So it is 6.67 minus 5. And similarly, we are resolving to get the normal in the x and y direction for the this side. So it is, if we are, this would be 1 by root 2 and 1 by root 2 normal. So it is 1 by root 2, and this is cell number 10. So it is next to that we do not have any cells. So it is W10 minus 0, and the point would be y-axis point would be 6.67, and the boundary point would be 7. And similarly in x-axis it would be 0.67 and the boundary point would be 1. The boundary point in the sense this. So here if we are marking one, like if we get the exact midpoint of this, that would be since it is 6 and 8 in the y direction, that would be 7, and it is 0 and 2 in the x direction, it is 1. The coordinates alone are interchanged here, sorry for the trouble. So in the similar fashion, if we are solving for equations for all the cells separately by using the boundary conditions too, we will be getting one equation for each cell. The calculations are shown over here. Like for every cell, like 1, 2, 3, and 4, 5, 6, 7, 8, 9, 10. So for each cells, we can solve in this similar fashion nx dou w by dou x plus ny dou w by dou y. For summing up all these things, we get one equation for one cells. And the procedure for 2 and 3, 5, 6, and 8 cells, eighth cell would be similar to what we have done for 1, and 4, 7, 7 and 9 cells would be similar to that of 4, and 10th cell we have also seen. So for solving all these cells separately, we are getting one equation. This is for cell 1, cell 2, cell 3, cell 4, cell 5, and this is for cell 4 and 5, cell 6, cell 7, cell 8, cell 9, and this is for cell 10. So we are getting 10 equations. So these are the equations that we will get when we solve all those cells separately using finite volume approach. So the question 4, what they have asked is, you wish to solve for the velocity field for fully developed flow through the triangular that using the grid shown in figure 2, you discretize the governing equations using finite volume method and obtain a set of algebraic equations. How many algebraic equations will you need to solve simultaneously if the walls have zero wall boundary conditions? So from this we can say that since we have like there are 10 cells, will be getting each equation for each individual cells. So the answer to this question is option 3, that is 10 equations will be getting. Just a quick recap, like in finite volume approach, what we are doing is the direction cosine of the outward normal. We are using outward normal for each side. That is, for if we are using going by this side, the direction cosine would be outward normal. That is towards the left, and this is towards the down, and this would be somewhere to this direction. So only we are resolving it in x and y direction, and the direction cosines are obtained from the geometry of the each side. That is, we are obtaining in geometry of the each side, while the gradients are evaluated at midpoints of each side using values of the cell and those of the neighboring cells or boundary conditions. This is what we have seen, where we evaluated the gradient, that is dou w by dou x or dou w by dou y, by taking the values from the cells between the midpoints, that is midpoints of each side, using the values from the cell and the boundary neighboring cells, or the cell and the boundary conditions, that is the walls we have used. So this is what using finite volume approach we can solve these. uh, in just a minute, I'll just change this because this is pretty confusing. I guess it is fine now. So we'll go back to the presentation. So we are getting 10 equations. These are the equations. This is for cell 1, cell 2, cell 3, cell 4, cell 5, cell 6, cell 7, cell 8, cell 9, cell 10. So on solving and like on discretizing all those using finite volume approach, we will be getting 10 algebraic equations. These equations should be solved simultaneously to obtain the results. So, question 4 is over. Question 5, it is given that for the grid shown in figure 2, if the algebraic equations resulting from the discretization of the governing equations are arranged in the form of matrix equation, then the non-zero coefficients in the coefficient matrix will not have a diagonal structure, will have a tridiagonal structure with three adjacent diagonals including the main diagonal, have a pentadiagonal structure with five adjacent diagonals including the main diagonal, have a pentadiagonal structure with zero diagonals between with zero diagonals in between some of the non-zero diagonals. So the question is, if the algebraic equations resulting, we have got 10 different equations, right? So if the algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix equation, then the non-zero coefficients in the coefficient matrix will. So if we are putting it in the form of, like, we have got these many equations, these are having w1 to w10 coefficients. So like w is equal to some constants, ax is equal to b. If we are writing it in that format, the question is asking how many resulting from the non-zero coefficient, I mean what kind of matrix they will form. So in order to understand that, we'll just plot these in a diagonal structure. That is, this is like from here it is starting, that is -3 to -6.4. For this is cell 1, cell 2, cell 3, cell 4, cell 5, and this is in w1, w2, w3, w4, w5. So if we are writing it in the AW is equal to some constant, here we are getting like we should see what sort of diagonal structure we are having. If it is pentadiagonal, the entire diagonal will have elements along with the elements in this next row and the row below and row above diagonally. But if we are seeing there are zero elements in the bottom diagonal, and in similar way there are zero elements in the top diagonal too. So it is not forming tridiagonal structure. Pentadiagonal structure, obviously it is not forming pentadiagonal structure. Um, some with zero diagonals in between some of the non-zero diagonals. So it is asking like either it is pentadiagonal structure together with everything, or there are some gap in between and there are pentadiagonal elements. So either way it is not at all forming any pentadiagonal structure, because immediately the row below and the above has some zero coefficients. So the answer to this question is they do not have a diagonal structure. Uh, so in question 6, it is asked that for the grid shown in figure 2, if the algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix equation, then the number of rows having exactly 3 non-zero coefficients in the coefficient matrix is. So in this questions, it is asked like, if algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix equation. That is, we are arranging the discretized equations that we have got in the form of a matrix. That is how we arranged in the previous question, like in the format of AW is equal to B. Then the number of rows having exactly 3 non-zero coefficients in the coefficient matrices. It is asking like number of rows having exactly 3 non-zero coefficients in the coefficient matrix. So basically this is the coefficient matrix. So in the question, it is asked like number of rows having exactly 3 non-zero coefficients. So if we count that, it is seen that in row 1 we are having 3 coefficients, that is minus 3.5 and zero point 0.5. So row 1 we are having. If we are looking into row 2, it is like there are more than 3 non-zero coefficients. In row 3 it is like more than 3, almost 4. In row 4 it is less than 3, that is only 2 are there. And in row 5 it is 4, whereas in row 6 also it is more than 3. In row 7, however, we can able to see that there are 3, that is 0.6, 0.6 and minus 5.5. So one more row, and in row 8 it is 4, that is zero point 0.5 minus 2.7, 0.6 and 0.6. And in row 9 it is, we are getting only 3 non-zero coefficients, that is 0 0.6, 0.6 and minus 5.5. In row 10 we are able to get 0.6 and minus 6.4. That is 2, it is less than 3. So the number of rows having exactly 3 non-zero coefficient is this is first row and seventh row and ninth row. So it is 3 rows. So the answer to this question is number 3. So in question 7, we will move on to question 7. For the grid shown in figure 2, if the algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix equation, do you expect the diagonal dominance condition will be satisfied? Uh, so the given options are yes, the equations can be ordered in such a way that the diagonal dominance conditions will be satisfied. In option 2, it is given no, the diagonal dominance conditions cannot be satisfied no matter how the equations are ordered. And option 3, it is we cannot say a priori about the diagonal dominance condition. Basic, and in option 4 it is diagonal dominance condition is irrelevant for unstructured grids. Basically by solving the in CFD, what we do is we discretize the given system, and we'll get a number of algebraic equations which we solve using some mathematical numerical approach. From numerical approach we'll get the solutions. So most of the numerical techniques will check for the diagonal dominance to ensure the convergence in those problems. So it is asked like we are getting a matrix similar to this. So in this, by looking itself, we can say that the diagonal elements are having some sort of dominance, and if arranged, they will give a diagonal dominance conditions will certainly be satisfied. So the answer to this question is yes, the equations can be ordered in such a way that the diagonal dominance conditions will be satisfied. Uh, we'll move on to question 8. In question 8, it is asked that, uh, just a minute. In question 8, it is asked that if the shaded triangle in figure 3 is a right-handed isosceles triangle, then the direction cosine of the vertical side are. So basically, this is the figure 3. So there is a shaded triangle in between. They are saying that it is a right-handed isosceles triangle. The direction cosines of the vertical side are, so this would be in this direction, that is we are looking for the direction cosine in the outward normal of that side. So since we are considering the vertical side, the outward normal to this side would be facing this direction, so it would be minus 1 comma 0, that is nx would be there, so it is minus 1 comma 0. So the next problem is similar to this problem. If the starred triangle in figure 3 is a right angled isosceles triangle with vertical side of length A. So this is a starred triangle. This is a right angled isosceles triangle with vertical side of length A. So we are just using this triangle over here, and vertical side it is given that it is length is A, and in the horizontal side it is given that the length is B. So the direction cosine of the diagonal side are. So it is right angle isosceles triangle. It is given that we are required to find the direction cosine for this diagonal side. So the diagonal side, the direction cosine would be in this direction when we are looking for the outward normal to it. So we must resolve it in x and y. So basically, since this is a right angle isosceles triangle, this would be 45 degree and 45 degree each. So obviously this is A and B. The diagonal would be A square plus B square, root of A square plus B square. So this would be like if we are forming a triangle and resolving it, this direction would be like if we are using cos 45, for this it would be b by root of a square plus b square, and in this vertical direction that would be a by root of a square plus b square. So the answer to this question is, they are given four options. In the first it is a by root of a square plus b square, comma b by a square plus b square. This is not true because it is interchanged. The x and y are interchanged in this. And in option 2 it is given that minus a by a square plus b square, I mean root of a square plus b square, comma b by a square plus b square, I mean root of a square plus b square. So this is also false because both are interchanged and the signs are also wrong. And in option 3 it is given that minus b by a square plus b square, I mean root of a square plus b square plus a by root of a square plus b square. This answer, the sign is wrong. Sign is for the direction cosine is wrong. And in option 4 it is pakka, like b by root of a square plus b square, comma root of a by root of a square plus b square. So the answer to this question is option 4. In question, we'll move on to question 10. In deriving the set of algebraic equations for the grid shown in figure 3, boundary conditions are not used for how many cells? Um, so it is given that we are using algebraic we are deriving a set of algebraic equations for the grid shown in figure 3. So this is the triangular duct and the grids are arranged in this way, and we are asked like for how many cells, that is boundary conditions are not used. So if we look into these cells, boundary conditions would be applied in these zone, I mean this this boundary and this boundary. So the cells adjacent to this boundary would be definitely having a boundary condition applied. So if we neglect these cells and count the remaining cells, we can see how many cells are not using boundary conditions. So it is this cell is using boundary conditions. So this cell is also using, and this cell we are not using. That is, this one is not using any boundary condition. And for example, so the cell is using, I mean the cell is not using boundary condition. I mean we'll mark it as 1. Um, It's okay. We'll just go with the text box for now. So the cell is not using, and similarly, this cell is also not using. So in deriving, okay, uh, in deriving the set of algebraic. Okay. In deriving the set of algebraic equations for the grid shown in figure 3, boundary conditions are not used for how many cells? So in this it is seen like we'll we'll be using boundary conditions for all those cells associated with the boundary. So leaving out all those cells like this cell, this cell, this cell, and this cell, and this cell, this cell. All these cells if we are leaving out and marking only those cells that are within not using boundaries, boundary conditions, we can get 1, 2, 3, 4, 5, 6 and 7 cells. So there will be 7 cells that are not using boundary conditions in deriving the set of algebraic equations for the grid shown in figure 3. So this is figure 3, and in deriving the set of algebraic equations for the grid shown in figure 3, we are not using boundary conditions for 7 cells. Next is we'll move on to one more case. Here it is given that choose the correct answers from the options below, and this is the case that is given. So in this case it is given that steady flow through a duct of rectangular cross section with width W, height H and length L in the Z direction. Planes A and D are the inlet and the outlet planes, while planes B and C are at distance of 0.5 times L and zero point 0.9 times L respectively. Normal velocity at inlet is uniform. Also, it is given that length is very much greater than width, and also length is very much greater than height. One can expect the flow to have a fully developed by plane C. There are few points that can be noted when we are looking into this picture. Uh, First is it is given that length is very much greater than length is in z direction. So it is length is very much greater than the width and the height, that is in x direction and in the y direction. And plane A is the inlet and plane D is the outlet. So any fluid, it is flowing through this duct of rectangular cross section, having this width and this height. So A is the inlet and D is the outlet. B and C are in between these inlet and outlet planes. So considering that B is somewhat in the midpoint, and that is if length is L, B is at 50% of length L, and C is almost 90%, zero point 0.9 times L. Um, so it is given that normal velocity at inlet is also uniform. So considering all these things, like the flow is also the flow is expected to be have a fully developed by plane C. By plane C, it is given that the flow is almost fully developed. So this is the case for this following set of that is observed in the following set of problems. Based on this case only, the questions are asked in this. Um, so that's it. It is a simple case where flow is through a rectangular cross section with inlet plane A and outlet plane D, and in between planes B and C, B is at the midpoint and C is towards the end, and the width is in x direction and height is in y direction, with Z, that is in Z direction, that is length. So we'll ask what type of questions are asked in this problem. Also, it is given that length is very much greater than width and height both. So, how many partial differential equations do we need to solve to for this system? It is like we have one continuity equation and three momentum balance equation whenever we are solving any uh, flow related problem. So that would be four. So it is not 1, 2, 3, or the answer to this question is 4. So it is given that if W is equal to 0.04 meter, we'll just take a 5 minutes break before proceeding with this problem. So yeah, we'll continue now. So in this question, it is asked that if W is equal to 0.04 and H is equal to 0.03 and length is 1.5 meter with inlet velocity for the with inlet velocity for a Reynolds number of 1000 would be about. So in this question it is asked that they have given the width in this problem of the rectangular duct and the height of the duct 2 is given, that is it is given as 0.03 meter, and the length of the duct is also given 1.5 meter. So it is asked that inlet velocity for an inlet Reynolds number of 1000 would be what? So since the problem is dealing with the rectangular duct, the general formula for Reynolds number would be R Reynolds number is equal to rho V d by mu, where we know the flow is with considering it to be water with we know the rho, that is 1000 kg per meter cube density for the water, and viscosity would be 1 into 10 power minus 3 per kg per meter second. So in this case remaining things are V and D. So V is asked in the question. So for diameter, in general, if it is a circular duct, we use the diameter of the circular column or tube or something. But since this is a rectangular duct, so we need to calculate the diameter. So in general, it is that for rectangular duct, we use the formula rho V dH by mu, where dH is nothing but hydraulic radius, hydraulic diameter. So in for hydraulic diameter, it is the formula is nothing but 4 into cross-sectional area of the flow by divided by wetted perimeter. Wetted perimeter. So it is that 4 into WH. W is nothing but the width of the flow domain, and H is the height. That is, this is height and this is width. So this gives the cross-sectional area of the flow domain. So it is 4 into WH by 2 times of W into H. On substituting all these factors, that 2 times 2 it's cancelled, and W is 0.04, H is 0.03. So 2 times of 0.04 into 0.03 divided by W plus H is 0.04 plus 0.03, it gives 0.07. So it would be DH would be 0.034 meter. When we do this calculation, we obtain the hydraulic diameter as this. So from this we can use the Reynolds number formula and calculate the sorry inlet velocity. So doing those things, we get like Re is equal to rho V dH by mu. Now we know the Reynolds number as 1000, rho is 1000 kg per meter cube, and V is still unknown, and dH we have calculated now to be 0.03429 meter divided by mu, that is 1 into 10 power minus 3. So on substituting all these things, we get the velocity to be 0.0291 meter. Approximately it is 0.03 meter per second. Sorry, it is 0.03 meter per second. So the question is, if W is equal to 0.04 and H is equal to 0.03 meter, W and length is 1.5 meter, inlet velocity for an inlet velocity for an the inlet velocity for an inlet Reynolds number of 1000 would be what? So it would be about 0.0291 or 0.03 meter per second. So in the option it is given 0.03 meter per second, which is the correct answer, and it is not 0.3 or 3 or 10 meter per second. All these answers are not appropriate. So the answer is 0.03 meter per second. In question 3 for the second week, week 3, it is given that the continuity equation for this case can be written as There are four set of continuity equation. This is flow through a rectangular duct. So in general, we know the continuity equation. So we have also seen the continuity equation for in the uh, very first problem. While solving the very first problem, we have seen the continuity equation. It is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. In a similar way, when we are substituting the, when we are using the same concept, in this problem also, it is we get that in first equation it is given that dou u by dou z plus dou v by dou z plus dou w by dou z is equal to 0, which is false because it is not dou u by dou z or dou v by dou z. Only this option is correct, that is dou w by dou z. In second, it is given dou u by dou y plus dou v by dou z plus dou w by dou x. All things are interchanged. It is not in the same, like, so this option is also false. And in option 3 it is given dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So this is the continuity equation that we are using in this. And in option 4 it is dou u by dou x plus dou u by dou y plus dou u by dou z. It is not the same velocity in all three directions, so this is also false. So the answer to this question is option 3, that is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. The momentum balance equations in the x direction can be written as, so in the x direction, we can similarly go on checking the previous case where we have studied the uh, governing equations. Sorry. So it is like you do in the steady state, the first term obviously goes to 0, and it like dou u by dou t or dou v by dou t dou u by dou t. So the one in the x direction, if we are considering, this is the momentum balance equation, whereas this is a continuity equation. So it is dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus dou p by dou x plus rho g plus mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. So since we are we'll see what the answer to this is obviously option 3, and we'll see why 1 and 2 are not applicable. So in the first, it is given that u dou u by dou x plus v dou v by dou y plus w dou u by dou z is equal to minus 1 by rho dou p by dou x mu plus mu by rho dou square u by dou x square plus dou square v by dou y square plus dou square w by dou z square. And the first thing is, it is dealing with in the x direction, so it should be constantly dou u everywhere in the, it is not dou u, I mean here it is dou v is coming, so this is false. And also it should be u here also, so the option 1 is wrong because of that. In option 2, it is given that u dou u by dou x plus v dou u by dou y plus w dou u by dou z. So this LHS is correct in this equation, and is equal to minus 1 by rho dou p by dou x plus mu by rho dou square u by dou x square plus dou square v by dou y square plus dou square w by dou z square. In the RHS, it is not u velocity is not maintained. So in first case, both LHS and RHS were false, whereas in second case, LHS is correct but RHS is wrong. In option 3, it is given u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus 1 by rho dou p by dou x plus mu by rho dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. So obviously the option 3 is the correct answer. And we'll move on to question 5. An appropriate boundary condition at plane D is given by dou P by dou Z is equal to 0, dou W by dou Z is equal to 0, velocity is equal to V in. So which of the option is correct, or none of the three is correct? So on seeing that, we can say that since we'll go and see, check in this, A, B, C and D. D is the outlet plane. That is the last plane at the exit, where we have a completely fully developed flow. So it is not dou P by dou Z is equal to not 0, whereas velocity would have attained a steady state or the fully developed flow. So it would be the same in at plane D. So dou W by dou Z is equal to 0. That is correct. Flow is fully developed by plane C itself, almost. So at plane D there is no point. It is the same. So dou W by dou Z is 0. It is not varying with respect to Z or with respect to length of the duct. And velocity, it is not equal to velocity inlet. V in is the velocity at the inlet plane, that is plane A. With what velocity it is entering into the plane A. So the answer to this is dou W by dou Z is equal to 0. We'll move on to question 6. In question 6, it is given that which of the following statements is true about pressure at the midpoint of plane C? Pressure is greater than pressure at the inlet. Option 1. Dou P by dou Z is equal to 0. Dou P by dou Z is equal to constant. So, the pressure at the midpoint of plane C. So, this is plane C where the flow is almost fully developed. It is given that one can expect the flow to have a fully developed by plane C. So obviously a flow occurs in the direction of where pressure drops. So it is not, pressure is not greater than pressure at the inlet, and also pressure is not constant, or it is not even, the pressure gradient is not 0, pressure gradient is not constant. So it would be varying, and that's why it is like option 1 is not true, option 2 is not true, option 3 is also not true, none of the 3. That is the correct answer. So which of the following statements is true about velocity at the midpoint of plane B? So it is given that which of the following statements is true about the velocity at the midpoint of plane B. Plane B is nothing but the second plane immediately at the after inlet plane. It is not immediately after that. It is at the midpoint between the plane A and plane D, because it is given that length, the rectangular duct length is L, and plane B is situated at the point at the distance of 0.5 L. So on using these things, what it is given is that which of the following statements is true about the velocity at the midpoint of plane B? Uh, W velocity is greater than velocity inlet, that is inlet velocity. Dou W by dou Z is equal to 0, or dou W by dou Z is equal to constant. By plane B, it has not attained fully developed flow. It is moving towards fully developed flow. So the profile would be almost like this, where at this midpoint of the plane B, we know the profile to be parabolic. So the velocity would be higher towards the flow direction. So the W velocity, or the velocity in the length direction, would be higher than the inlet velocity, but it would not be constant in the Z direction, or the gradient also would not be constant. So the answer to this question would be option 1. That is, W velocity is greater than V inlet. We'll move on to the question 8. Mm, we'll take 2 minutes break before starting this. So in question 8, it is asked like, which of the following statements is true for a Newtonian fluid? In option 1, it is given that viscous stress versus strain relation is linear and viscous stress is proportional to the local deformation rate. Viscosity is independent of shear stress. So it is asked like, which of the following statements is true for a Newtonian fluid? So what is Newtonian fluid? In Newtonian fluid, it is that we all know its velocity to be constant, and general definition would go along the line like where the viscous stresses are linearly correlated to the local strain rate. That is the stress is directly proportional to the rate at which the fluid deforms with respect to time. So we can define Newtonian fluid like that, which obeys Newton's law of viscosity, which states that the stress is directly proportional to the strain rate. From this it is asked like, which of the following statements is true for a Newtonian fluid? So in option 1 it is given that viscous stress versus strain relation is linear. This is not true because viscous stress is directly our viscous stress is versus strain rate, that is the rate of deformation is linear. It is not a strain but it is strain rate. Viscous stress is proportional to the local deformation rate. This point is correct. Viscous stress is proportional to local deformation rate. That is the definition we use for stating the Newtonian fluid. So this option is correct. And in option 3, it is given that viscosity is independent of shear stress. Well, it is viscosity is constant for the Newtonian fluid. It is independent of the shear stress. So option 3 is also correct. For this question, the answer is option 2 and option 3. So 1 and 2 is given for option 1, whereas 1 is not true. 2 and 3, it is option 2. Answer is option 2. In 3 it is given 1 and 3 or 1, 2 and 3, whereas the first statement is wrong. So all these statements are not applicable. Newtonian fluid is nothing but all those fluids which generally obey Newton's law of viscosity, where viscosity is not affected by shear rate or shear stress, where everything else remains the same. The common examples would be water, air, or some common fluids that we use. So basically, the viscous stress versus is directly proportional to the local deformation rate, and the viscosity is independent of the shear stress, or it remains a constant. So it is given that in question 9, it is given that a fluid element in a steady laminar fully developed flow of an incompressible fluid between two infinitely long and wide plates undergoes which type of strain? So it is given that consider flow between two parallel plates. That is consider flow between two parallel plates that are infinitely long. A fluid element in a steady, laminar, fully developed flow of an incompressible fluid between two infinitely long and wide plates undergoes which type of strain? So if it is between infinitely long and wide plates, there are three different strains that are given: rotational strain, extensional strain, or shear strain. Since the flow is between two parallel plates, there will obviously be some rotational strain that is occurring, but there won't be any extensional strain. That is, there won't be any extension or elongational thing happening in the flow. So option 2 is not right. Whereas shear stress will obviously be, shear strain will be there because of which the fluid motion, because of shear stress only fluid will be moving, and so there will be shear strain. So 1 and 3 are right. So in the options it is given that 1 and 2, 2 is false, so it is not true. 2 and 3, here also 2 is false. 1 and 3, this is correct. So answer is option 3. In option 4 2, it is given that 1, 2 and 3, whereas 2 is false. For a fully developed flow, the state momentum balance equation reduces to which of the following equation? Um, it is given that for a fully developed flow and the flow is steady state. So first option is dou square W by dou Y square is equal to 0, or dou square W by dou X square is plus dou square W by dou Y square is equal to 0. Or else in option 3 it is given that dou square U by dou X square plus dou square V by dou Y square is equal to 0. And option 4 it is none of the three. So the flow here is fully developed flow and steady state flow. It is asked that momentum balance equation reduces to which of the following? So okay, in general it would be like this would be the momentum balance equation where steady state, so this would become 0, and this term is what they have given, so obviously these terms would be a constant, they would be something remaining. So it is not dou square W by dou X square plus dou square W by dou Y square would be constant. So it is not that would not be varying like dou square v by dou x square plus dou square v by dou y square. So this is answer. This option is also wrong, and this is also obviously wrong. And so the answer to this question would be none of the three. All the three above three options are false. So it is none of the three. So thank you. These are the 26 questions that we have seen today. If anyone of you is having any doubts, please let me know. Or else we'll just quickly recap what are all the concepts we have seen today before winding up the session if no one is having doubts. Let's wait for 2 more minutes for doubts clearing. So, let us just quickly go through what are all the concepts we saw today. The first one we saw is flow through triangular duct. Based on that, we have solved few problems. So, the different set of discretization schemes are given in three different figures, and based on that, we have seen problems. So, the first question was basically so the first question was asking about the governing equation for a steady laminar fully developed flow field through the triangular duct. For that, we have seen that it would be del dot del u is equal to constant. Uh, these are the this is the governing equation which reduces to del dot del u is equal to constant when we are using the steady laminar, all those conditions applied. And in the next question, it was asked like similar to that steady laminar fully developed flow field through the triangular duct as in figure 1, and what are the admissible equations. So we have seen three different equations were given, and it should have been like none of the three were correct. So the answer to that was none of the above. And it is in question 3 also, steady laminar fully developed flow field through the triangular duct, and which of the following equations were applicable. So for this we have seen that these are all the equations that are applicable for the flow through steady laminar fully developed flow field through the triangular duct. So from this it is observed that the option is del dot u is equal to 0 is correct. Del p is equal to constant, it is not 0. Whereas del dot del p is equal to 0. So 1 and 3 are correct, whereas 2 is wrong. And you wish to solve for the velocity field for fully developed flow through the triangular duct using the grid as shown in figure 2. Figure 2, there is a specific grid, it is shown. So if the flow is through the triangular duct, how many algebraic equations are needed to be solved simultaneously to get the solutions. That is what is asked in question number 4. So they have given that, so discretize the equations using the finite volume method. So basically, in finite volume method, we have seen how the method will be carried out. Basically, it is like nx into dou w by dou x plus ny into dou w by dou y, and on all these sides. That is, if it is a triangle we are considering for 3 different sides, we should be uh, using this, and summation of all the sides for that particular cell will will give us C into area of that particular cell. This is for the triangular grid. So it would be like summing up all these things and would be equal to area times some specific constant C. That is how we proceed with the finite volume method. In finite volume method, we use the direction cosines nx and ny. In which direction those should be used is, normally if it is this phase, that would be in outward normal direction, the direction cosines would be used. And whereas for getting the gradients, it would be evaluated at the midpoint of the cells. I mean, between two cells it would be evaluated. So obviously it would be, if these two are the cells under consideration, it would be midpoint of this cell and this cell. Whereas if there is, if this is this cell and we are considering in this direction, it would be midpoint of this cell versus the boundary point. That is what is given in this line. That is, the direction cosines are obtained from the geometry of the each side, while the gradients are evaluated at midpoints of each side using values of the cell and those of the neighboring cells, or else the boundary conditions. So we have used this finite volume method to get the figure 2 discretized. So basically we have put 8 different points. Since we are using midpoints, we have used each cell to be 2 in dimension. So in that way, we have put grid points for all those things and just mark the cells for our convenience. There are 10 cells. So for each cell we have written different equations. So we have seen how to write the equations by considering the writing equation for cell 1, cell 4 and cell 10. That is, before that we need to calculate the centroid of the cells. For square based cells, the center point would obviously be easy because it is like 2 in dimension here, 2 in dimension here. So the midpoint would be 1, 1. That is what we have given for cell 1. It is the 1, 1. Whereas if we are considering the triangle 4, sorry, that is in triangle 4, that is the corner cell, it is given that the centroid of the triangle would be summing up all the x coordinates and the y coordinates separately and dividing by the 3 for x and y. And that would give the centroid of this cell. So for x will be 6 plus 6 plus 8 divided by 3. 8 divided by 3, that is giving 6.67. Whereas for y it is giving 0 plus 2 plus 0 divided by 3, that is giving 0.67. So for centroids of all the cells are also calculated. For And after calculation of this, we are using nx into dou w by dou x plus ny into dou w by dou y and summation of all those things in the left hand side. Considering the cell 1, that is this corner cell, we are using that. It is minus 1. We are using direction coefficient in 4 different, like since there are 4 different cells, 4 different phases, we are separately writing things for that. In this direction, it would, for this phase, the direction cosine would be in the outward normal of this. That is, it would be left pointing. So it would be minus 1. This is W1 and this is, there are no cells to the left hand side of the cell 1. So we are using the mid boundary condition. That is W1 minus 0 and divided by 1 minus 0. That would give us the value in this phase. Whereas in this bottom phase also it would be minus 1 into W1 minus 0. That is, we are using midpoint and the boundary condition. W1 minus 0 by 1 minus 0. This is y. Whereas in this x direction, it is between cell 1 and cell 2. In cell 2, the midpoint would be 3. So it is 3 minus 1. Whereas the direction is positive, so it is 1. W2, that is for cell 2 minus cell 1. Similarly, the cell above cell 1 is cell 5. So it is W5 minus W1 by, it is 3. 3 minus 1. So in this similar fashion, we can get all the values for the square based cells similar to the calculation shown here. And for cell 4, it is that uh, we are using it, since it is a triangular cell. For this cell and this cell, we can easily write it as, this cell it is in the negative x direction, so it is minus 1. This is cell 4, W4 minus, this is cell 3, W3. The midpoint of this cell is 6.67 minus the midpoint of the adjacent cell is 5. That is 6.67 minus 5. Similarly, for bottom cell, we can write as W4 minus 0, because there are no cells at the bottom, and it would be midpoint would be 0.67 minus 0 and it would be minus 1. But for this direction, that is the diagonal of this triangle, we need the direction cosine would be in this direction, so it must be resolved in the x and y. When we are resolving it, we get the x and y values to be 1 by root 2, 1 by root 2, and it would be like, say, if we are going in this direction, it would be W4 minus 0, that is in the boundary, and the midpoint of the boundary would be 7. So it would be 6.67 minus 7 in the x direction versus 0.67 minus 1. In the midpoint in the y direction would be 1. So in this way, we can write for cell 4, and it would be C into half into base into height for area for the triangle. In a similar way, we can write for cell 10 also, that is the topmost cell, where we have given these equations. Like similar fashion, we can resolve it, for x this direction and this direction, we know to formulate the equation. And for the diagonal, we know the direction cosine would be this way, that is outward normal. So we are resolving it into nx and ny. The normal is resolved into nx and ny. So based on that, we get the normal direct values to be 1 by root 2 and 1 by root 2. And similar to this, we use a calculation. Similarly, for all the triangular cells, we can formulate algebraic equation. When we are simplifying these terms, we get the algebraic equation. For example, these are the number of cells. For cell 1, we are using this equation, and we are simplifying it to this form, and W1, W2, like that, we are getting an algebraic equation. So similar manner, if we write equation for every cell, we are having 10 cells, so we'll be getting 10 different equations. That was what was asked in question 4, that is how many equations would be obtained. So the answer to that question would be 10 equations would be obtained. In question 5, it was asked that if the resulting algebraic equations are put in the form of a matrix, how many non-zero coefficients, the non-zero coefficients, would they be forming any special matrix structure? So when we wrote these equations in the form of this is like w1 w2, we had so many coefficients, so we are this is the coefficient matrix for that a w is equal to constant. For example, this is w1 w2, we have removed the coefficients and put separately the coefficient matrix from w1 to w10, since we are having 10 different cells, and in the right hand side we were having constants. So this is AW is equal to C. When we formed the matrix, we were able to see that it was not forming any diagonal structure. So that it was not forming a diagonal structure. Also, how many number of rows having exactly 3 non-zero coefficients? When we counted from the simplified thing, we were able to see that there were these three, 1, 7 and 9. All these rows were having exactly 3 non-zero coefficients. For example, 1, 2 and 3 in this first cell, and in the 7th cell we were able to see 1, 2 and 3, and in also in 9th cell we were having 1, 2 and 3. So exactly three non-zero coefficients in three rows. Number of rows having exactly three non-zero coefficients in the coefficient matrix is 3. Option 2, that is 3. Uh, so it is asked that if the algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix equation, were we expecting any diagonal dominance condition will be satisfied? Yes, the equations can be arranged or rearranged so that the diagonal dominance conditions will be satisfied. Uh, that was the answer to the question number 7. And also and then we have moved on to figure 3 and analyzed figure 3. In figure 3 it was given that um, if the shaded triangle in figure 3 is a right-handed isosceles triangle, then the direction cosines of the vertical side would be, so there were many different triangles given in this figure 3, which the shaded one is the right-handed isosceles triangle. So the direction cosine of the vertical side. The vertical side is this one, so the direction cosine would be in this direction. So that would be minus 1 comma 0. Of the vertical side would be minus 1 comma 0. On the main thing is direction cosine should be in the outward normal of that direction. So the outward normal to this direction would be this way. So the answer is minus 1 comma 0. Uh, so in question 9, it is asked that if the starred triangle in figure 3 is a right-handed isosceles triangle with vertical side of length A and horizontal side of length B, then the direction cosines of the diagonal side are. So basically this is a starred triangle. They have given this is a right angled isosceles triangle. So we are just using this equation. Um, we are assuming, I mean, these angles would be 45, 45 since it is an isosceles triangle, and right angled one, so it is 90 degree. And the vertical side is A and the horizontal side is B. And this is the diagonal side for which they have asked the directional cosine. So the outward normal would be in this direction. So when we are resolving it, the directional cosine nx and ny would be this. So basically this would be like cos 45 would give this value in the horizontal direction. So that would be cos 45 is equal to this diagonal would be a square root of a square plus b square. So summing up, putting together, we will get the nx to be b by root of a square plus b square, and in the vertical direction it would be a by root of a square plus b square. So the answer is option 4, where we have the correct thing, that is b by root of a square plus b square plus root of a by root of a square plus b square. So in question 10, it is asked that in deriving the set of algebraic equations for the grid shown in figure 3, this is figure 3, the boundary conditions are not used for how many cells? So obviously the sides that are adjacent to the boundaries will be using boundary conditions. So we must count the number of cells in the system where they are not placed next to the boundaries. So obviously this is 1, 2, 3, 4, 5, 6, 7. 7 cells are not using boundary conditions. All other cells are using boundaries. Like this one is having this boundary, this one is having vertical boundary, vertical boundary, vertical boundary, and horizontal boundary as well. horizontal, and the diagonal, here diagonal, diagonal. So basically 7 cells are not using boundary conditions. So these were the questions from the week 2. So in week 3 problem, another different set of one more case was given, that in four, like this is a fluid was flowing through a rectangular duct where A and D are the inlet and the outlet planes, and B and C are in between planes, where B is at the midpoint, that is 0.5 times of the L, whereas towards C it is 0.9 times the L. So in this it is given that one can expect the flow to be fully developed by plane C. So this is the case given. So how many partial differential equations do we need to solve? It would be one continuity equation followed by 3 momentum equations, momentum balance. So it would be 4 equations should be solved. If W is given as 0.04 meter, and H is given as 0.03 meter, and L is given as 1.5 meter, with what would be the inlet velocity when the inlet Reynolds number is given as 1000. So this is the rectangular duct problem, and the flow is through the rectangular duct. So normally if it is a circular column, we use the Reynolds number as rho v d by mu, where d would be the diameter of that circular duct. But in rectangular duct, we need to calculate the hydraulic diameter, which would be given as 4 times the cross-sectional area of the flow divided by the wetted perimeter. So substituting this in the formula and substituting the values, we get the dH, and here the Reynolds number would be Re is equal to rho v dH by mu. So substituting this dH in here, we get the V is equal to 0.03 meter per second. So the continuity equation for this case of flow through rectangular duct, it would be dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is a general case where all others were having different uh, velocity or different domains. So all the other options were wrong, and it is given the momentum balance in the x direction can be written as it would be momentum balance in the x direction. It would be like u direction velocity, or in the x direction velocity, u velocity would be given everywhere. That is dou u by dou x into u plus v into dou u by dou y plus w into dou w by dou z is equal to minus dou p by dou x plus rho g plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. So obviously it would be like option 3. In the first, LHS and RHS both were wrong, whereas in second option LHS was correct, but in the right hand side it was given individual velocities were given, like u, v and w were given, which is wrong. So and the answer is option 3. In question 5, it was asked what was the appropriate boundary condition at the plane D. Plane D is the outer plane where the velocity would have reached steady state, fully developed flow profile. So dou W by dou Z would be 0 at that point. Option is 2, and that is second one, dou W by dou Z is equal to 0. Which of the following statement is true about pressure at the midpoint of C? Pressure is less than, it is not greater than pressure at the inlet, because we know that the fluid flows towards the direction of lower pressure, whereas dou P by dou Z is neither constant nor it is 0. So the answer is none of the three. In question 7, it was asked that which of the following statements is true about velocity at the midpoint of plane B. Plane B is towards the center, that is 0.5 times of the length. So at this it would be like velocity at the midpoint would be higher than the velocity at the inlet, but it would not be 0, or I mean the velocity gradient would not be 0, or it would not be constant. So the answer is option 1 is the correct answer. So in question 8, it was about Newtonian fluid. In Newtonian fluid, those that obey Newton's law of viscosity, which states that the viscous stress is directly proportional to the local deformation rate or strain rate. Viscosity for Newtonian fluids would be constant. So it is three options were given. Viscous stress versus strain relation is not linear. Viscous stress versus strain rate relation is linear. Viscous stress is proportional to the local deformation rate. This is correct. Viscous stress is proportional to local deformation rate. Viscosity is independent of shear stress, which is also correct because viscosity remains constant. So the answer to this question would be option 2 and 3 both are right. So answer is option 2. So in question 9 it was asked that a fluid element in a steady laminar fully developed flow of an incompressible fluid between two infinitely long and wide parallel plates undergoes which type of strain? So that would be undergoing rotational strain and shear strain, whereas extensional type of stress or strain is not happening in this system. So 1 and 3 is the right answer. For a fully developed flow, the steady state momentum balance equation reduces to it is not, it would be constant. All other things are false. So the answer is none of the three. So these were the set of problems that we saw today. We'll, if there is no doubts, we'll close the session and we'll meet in next week with a different set of problems. Thank you. This was week two's and week three problems from this year thing. That is what like this year assignment problems. That is what we have solved. So next week we'll move on to next week. That is week 4 after the deadline is over. So thanks for today's thing, and we'll meet with week 4 problems next week. Thank you.